Semiconductor equipment manufacturing. Focus on deposition technologies. Welcome to this presentation on semiconductor equipment manufacturing, with a focused lens on deposition technologies. Deposition is a critical step in semiconductor fabrication, where materials are carefully layered onto a wafer to build the complex structures that define microchips. This overview will guide you through the essential equipment used in this process, the technologies that enable high-precision layering, and the roles of different tools in achieving uniformity, accuracy, and scalability. From traditional batch reactors to cutting-edge atomic layer deposition systems, we will explore the innovations driving performance in deposition. Our goal is to provide a comprehensive understanding of how deposition fits within the broader manufacturing ecosystem. Whether you're an operator, technician, engineer, or manager, this session will help you connect process fundamentals with the technology platforms used on the fab floor. Let's begin our deep dive into deposition systems and their vital role in semiconductor manufacturing. Introduction to semiconductor manufacturing. Semiconductors are materials that have electrical conductivity between that of conductors and insulators. The most commonly used semiconductor material is silicon, thanks to its abundance, stability, and electrical properties. These materials are the foundation of all modern electronics, enabling everything from smartphones to supercomputers. They drive essential technologies in computing, telecommunications, automotive systems, artificial intelligence, the Internet of Things, and cloud infrastructure. The global semiconductor industry now exceeds a market value of $500 billion, underscoring its immense economic and technological importance. The manufacturing process begins with wafer manufacturing, where silicon crystals are grown and sliced into wafers. Front-end processing follows, involving deposition, lithography, and etching to build structures on the wafer. Circuit formation includes creating transistors and interconnects. Finally, back-end processing covers testing, dicing, and packaging. Key facts. The standard wafer diameter is 300 mm. The most advanced nodes are at 5 nanometers, and the entire process involves over 300 individual steps. Importance of semiconductor equipment manufacturing. Semiconductor equipment plays a critical role in enabling the production of increasingly complex chips. As transistors shrink and chip architectures become more advanced, manufacturing tools must evolve in tandem. These tools directly affect chip performance and functional capability, determining whether a device can meet performance targets in real-world applications. Equipment precision also defines how densely transistors can be packed, which in turn impacts speed, power efficiency, and overall functionality. Advanced manufacturing tools are essential for producing leading-edge semiconductor nodes at 5 nanometers and below. To achieve this, precision requirements are extreme. Manufacturing processes must be controlled at atomic scales, often between 2 and 10 nanometers. Equipment precision influences 3 key factors: manufacturing yield, which is the percentage of working chips, performance characteristics like speed and frequency, and the power efficiency of final products. Without this level of control, modern high-performance chips simply could not exist. Importance of semiconductor equipment manufacturing. The economic impact of semiconductor equipment manufacturing is enormous and growing rapidly. In 2023, the global market for semiconductor manufacturing equipment surpassed $110 billion. This segment is projected to grow at a compound annual growth rate, or KGR, of 7 to 10% through 2030. Such growth underscores its essential role not only in the tech sector, but in global economic competitiveness. Countries investing in semiconductor equipment are better positioned to lead in advanced technologies and secure resilient supply chains. This equipment is also foundational to enabling the broader $500+ billion semiconductor industry, which supports electronics, computing, telecommunications, and more. A key insight is that deposition equipment accounts for approximately 18% of the entire semiconductor equipment market. This makes deposition one of the most important technology segments in chip manufacturing, with major implications for device performance, yield, and manufacturing cost at scale. Deposition in the semiconductor fabrication process. Deposition is a core step in semiconductor fabrication, positioned after oxidation and before photolithography. It involves adding thin films of various materials, such as dielectrics, metals, or semiconductors, using methods like CVD, PECVD, or ALD. These layers are essential for the chip's electrical and functional performance. The deposition process is repeated multiple times to build the complex, multi-layered architecture of modern integrated circuits. Each deposition step plays a critical role in controlling the chip's electrical, optical, and physical characteristics. Precise control over thickness and composition is key, with typical film thickness ranging from 5 to 500 nanometers. The uniformity target is extremely tight, between plus or minus 1 to 5%. A single chip may require 15 to 30 deposition steps. Different deposition techniques are chosen based on the specific material and required film properties. This process enables the integration of advanced functionality across multiple layers in microchips. Introduction to deposition processes. Deposition is the process of adding thin films of material onto a semiconductor wafer substrate. It plays a foundational role in semiconductor manufacturing. These deposited films can be insulating, conducting, or semiconducting, enabling the creation of various layers with specific electrical or structural properties. Deposition is critical for forming structural and functional elements, which are necessary for device performance. It also allows for control over the electrical characteristics of devices and supports the formation of complex, multi-layered structures. This is especially important in the development of transistors and interconnects. In fact, deposition steps are typically repeated 15 to 30 times during the fabrication of a complex integrated circuit. During the process, atoms or molecules adhere to the wafer surface, forming thin films with thicknesses ranging from nanometers to microns. Uniformity, thickness, and step coverage are key properties, while temperature sensitivity, deposition rate, and material compatibility are essential considerations. Major deposition techniques. There are several key deposition techniques used in semiconductor manufacturing, each offering distinct advantages depending on process needs. Chemical vapor deposition, or CVD, relies on chemical reactions from gas phase precursors to form thin films. Operating between 300 to 900 degrees Celsius, it provides good process control and moderate step coverage. Plasma-enhanced CVD, or PECVD, introduces plasma to activate reactions at lower temperatures, typically between 200 to 400 degrees Celsius. It offers very good control and good step coverage, making it ideal for temperature-sensitive substrates. Atomic layer deposition, or ALD, enables the formation of ultra-thin, conformal layers through sequential, self-limiting reactions. It operates at 100 to 350 degrees Celsius and delivers excellent control and coverage, especially in high aspect ratio structures. Physical vapor deposition, or PVD, uses physical means like evaporation or sputtering. While the temperature range varies, PVD offers good control but limited coverage, making it more suitable for simpler geometries. Chemical vapor deposition, CVD. Overview. Chemical vapor deposition, or CVD, is a process where gaseous reactants undergo chemical reactions on a heated substrate surface, forming solid thin films. This method enables precise material deposition, making it foundational in semiconductor fabrication. The process begins with gas delivery, where precursor gases are introduced into the reaction chamber. Next is thermal activation. The substrate is heated to temperatures between 300 to 900 degrees Celsius, which initiates chemical reactions. At the surface, these gases react to form solid materials through surface reactions. The atoms then deposit on the wafer, forming thin film layers, a step known as film growth. Finally, byproduct removal is critical. the exhaust system removes any unwanted reaction byproducts. Key equipment components include the gas delivery system, heating system, and reaction chamber. Supporting systems include vacuum control, automation through control systems, and safety systems such as gas detectors and emergency shutoffs. Chemical vapor deposition, CVD, overview. The chemical vapor deposition process relies on precise control of environmental and chemical parameters to form high-quality thin films. The process diagram begins with gas entering through the gas inlet. These gases undergo gas phase reactions and then interact with a heated substrate, supported by a heater below. As the chemical reactions occur at the wafer surface, a solid film forms and grows upward, while the exhaust removes any excess gas or byproducts. Several core operating principles govern this process. Temperature control is critical because it influences reaction kinetics and directly affects film quality. Pressure regulation, typically ranging from 0.1 to 760 torr, ensures optimal reaction conditions. Precursor chemistry plays a vital role in defining the final film composition. Gas flow dynamics must deliver reactants uniformly across the wafer. Finally, the reaction rate determines how quickly and uniformly the film is deposited and its ultimate quality. CVD, applications and advantages. Chemical vapor deposition is a versatile technique widely used in semiconductor manufacturing. One major application is the formation of dielectric layers, such as silicon dioxide, SiO2, and silicon nitride, Si3N4, which provide electrical isolation and surface passivation. CVD is also essential for creating gate oxides. These include high-K materials like hafnium oxide, HFO2, which are critical for the performance of advanced transistors. Interconnect layers are another important use case. Tungsten, W, is deposited to form contacts and vias between metal layers, enabling electrical connections. In memory devices, tantalum oxide, Ta2O5, is used to construct high-density capacitors, especially in DRAM technology. CVD supports a wide range of materials, including dielectrics, metals, and semiconductors. Examples include SiO2, TEOS, BPSG, Ta2O5, and TIN. This broad material compatibility makes CVD indispensable for building modern, high-performance integrated circuits. CVD, applications and advantages. Chemical vapor deposition, or CVD, offers several advantages in semiconductor manufacturing. First, it provides excellent step coverage, ensuring uniform film deposition even over complex 3D structures and high aspect ratio features. This capability is essential for advanced nodes and device miniaturization. Second, CVD produces high-purity films with precise control over composition. This makes it ideal for critical layers where purity impacts electrical performance. Third, CVD supports a wide range of materials. With appropriate precursors, it can deposit metals, semiconductors, and dielectric films, offering versatility across applications. However, CVD also has limitations. It typically requires high process temperatures between 300 and 900 degrees Celsius, which can damage temperature-sensitive substrates. Additionally, many CVD precursors are hazardous. Some are toxic, corrosive, or pyrophoric, necessitating robust safety controls. Finally, CVD systems are complex, involving sophisticated equipment for gas handling, temperature regulation, and vacuum maintenance. A pie chart illustrates market share by application. Dielectric layers dominate, followed by gate oxides, interconnects, memory devices, and others. Plasma-enhanced CVD, PECVD, overview. Plasma-enhanced chemical vapor deposition, or PECVD, is a modified form of traditional CVD that utilizes plasma to initiate and drive chemical reactions at reduced substrate temperatures. This allows deposition of films on temperature-sensitive materials. In contrast to traditional CVD, which typically operates between 300 and 900 degrees Celsius, PECVD can function effectively between 200 and 400 degrees Celsius. It combines plasma and thermal energy to lower the activation barrier, offering a gentler deposition process. PECVD also results in lower and more controllable film stress, though step coverage is rated as good rather than excellent. However, PECVD systems tend to be more complex than traditional CVD tools. Plasma plays a critical role in PECVD. It ionizes and dissociates precursor gases, forming reactive species like ions and radicals. These species enhance reaction kinetics, lower activation energy, and enable deposition at reduced temperatures. Plasma parameters also help tailor film properties. A key insight is that plasma supplies energy to break chemical bonds without needing high substrate heating. Plasma-enhanced CVD, PECVD. Overview. In the PECVD process, a gas is introduced into a vacuum chamber and flows across a powered electrode, which is energized by an RF generator, typically at 13.56 MHz. The energy from the RF power creates a plasma region between the powered and heated electrodes. This plasma activates the precursor gases, enabling film deposition at low temperatures. The operating pressure usually ranges from 0.1 to 10 torr, optimized for stable plasma and effective deposition. Key components of PECVD systems include the RF power supply that generates the plasma and a matching network to optimize power transfer. The showerhead uniformly delivers gases, while electrodes help sustain the plasma. Temperature control maintains proper substrate heating, and the vacuum system regulates pressure. Operating principles begin with plasma generation, where RF energy ionizes gases. Reactive species are formed for precursor activation. Ion bombardment enhances surface reactions. Lower temperatures enable more delicate processing, while film properties are tuned by adjusting RF power, pressure, temperature, and gas flow. PECVD, applications and advantages. Plasma-enhanced chemical vapor deposition is widely used across the semiconductor industry due to its ability to deposit films at lower temperatures while offering excellent control over film properties. One major application is in passivation layers, where materials like silicon nitride, SiNCs, and silicon oxynitride, SiON, are deposited to protect devices from contamination and physical damage. PECVD is also essential for depositing low-K dielectrics, such as SiOC films, which provide effective electrical isolation for advanced interconnect structures. Another important use is in the formation of thin film transistors, especially for display technologies. These often utilize amorphous silicon, ASIH, and polycrystalline silicon films. PECVD supports a broad range of deposited materials, including SiNCs, SiO2, SiON, ASIH, SiOCH, DLC, ALOX, and SiC, depending on process conditions and application requirements. Key market segments using PECVD include advanced logic devices at 30%, memory manufacturing at 25%, and display technologies at 20%, reflecting its broad commercial relevance and adaptability. PECVD, applications and advantages. Plasma-enhanced chemical vapor deposition offers several critical advantages that make it suitable for a wide range of semiconductor applications. One major benefit is its lower deposition temperature, typically in the range of 200 to 400 degrees C. This allows processing of temperature-sensitive substrates and contributes to a reduced thermal budget, enabling more complex manufacturing steps. Another key advantage is enhanced film control. Plasma parameters can be tuned to achieve precise control over film properties such as stress, thickness, and uniformity. This precision is vital for achieving reliable performance in advanced device structures. However, PECVD also has some limitations. Plasma damage is a concern, as ion bombardment can degrade the substrate surface or affect sensitive device layers. Additionally, non-uniform plasma is a challenge, particularly when coating large area substrates, as it can lead to thickness variations. Typical film thicknesses range from 10 nanometers to 2 microns, with less than 1% variation, offering high precision in deposition. PECVD, applications and advantages. Plasma-enhanced chemical vapor deposition, or PECVD, offers significant advantages in semiconductor manufacturing. A key benefit is its ability to deposit films at low temperatures, which is crucial for temperature-sensitive substrates. In the performance comparison chart, PECVD clearly outperforms thermal CVD in low temperature capability and deposition rate, achieving higher ratings on a scale from 1 to 5. PECVD also delivers strong results in step coverage, enabling uniform coatings over complex topologies. While thermal CVD offers slightly better film quality and process control, PECVD provides a good balance with acceptable performance in these areas. Equipment cost for PECVD is comparable, offering a favorable return on investment. The industry adoption rate underscores this value. 85% of leading semiconductor fabs have implemented PECVD due to its versatility and performance. The accompanying image illustrates a modern PECVD system, highlighting its role as a critical technology in today's advanced fabrication environments. What is ALD? Atomic layer deposition, or ALD, is a precision thin film deposition method that relies on sequential, self-limiting surface reactions. This enables atomic level control over film thickness and composition, which is critical for advanced semiconductor structures. Unlike CVD or PECVD, ALD operates through separate, pulsed exposures of precursors. Its reaction mechanism involves two distinct precursor steps, each followed by a purge. First, precursor A, such as TMA, reacts with the surface. Then, a purge step removes any unreacted material. Next, precursor B, like water, reacts with the modified surface, followed by another purge to complete one ALD cycle. This cycle deposits only 0.1 to 0.3 nanometers of material, ensuring layer-by-layer construction with angstrom-level precision. ALD excels in conformality on high aspect ratio structures and deep trenches. Though its process speed is slower than CVD, ALD's accuracy makes it ideal for complex 3D features in modern device fabrication. Self-limiting reactions, equipment components, and operating principles. Atomic layer. Deposition relies on self-limiting reactions to ensure precision. Surface saturation ensures precursors react only at available surface sites, while reaction termination means the process automatically stops when all reactive sites are occupied. This guarantees consistent growth. Each cycle deposits the same material amount. The result is extremely uniform films, even over complex 3D structures. Key equipment components include precursor delivery systems using heated sources or vapors, fast-switching valves for precise timing, and reaction chambers with temperature-controlled walls. A vacuum system manages pressure and exhaust, while inert gases like nitrogen or argon support effective purging. Control systems automate the entire sequence with high precision. Operating principles include maintaining a temperature window of 100 to 350 degrees Celsius, tight control of cycle timing, and operation at pressures between 0.1 and 10 torr. Precursor chemistry must support reactivity and volatility. Two key ALD variants are thermal ALD and plasma-enhanced ALD, each optimized for different process needs. ALD, applications and advantages. Atomic layer deposition plays a critical role in fabricating advanced semiconductor devices. Key applications include high K-gate dielectrics, such as HFO2, ZrO2, and Al2O3, which are essential for modern transistors requiring precise control with minimal thickness. ALD also enables the creation of conformal ultra-thin films in DRAM capacitors, especially within high aspect ratio structures. Additionally, TIN and TAN layers serve as barrier or liner layers for copper interconnects in back-end integration. The range of deposited materials spans oxides like ZNO and SiO2, nitrides like TIN and TN, and metals such as Ru and PAT. ALD's advantages include precision thickness control at the atomic level, conformality over features with aspect ratios exceeding 100.1, and high film quality. However, limitations include a slow deposition rate, typically 0.1, 0.3 nanometers per cycle, and precursor constraints. Not all materials possess precursors with the right volatility and reactivity for ALD processes. ALD, applications and advantages. Atomic layer deposition achieves the highest conformality among thin film deposition methods. The conformality comparison chart shows that ALD delivers close to 100% step coverage, far exceeding PECVD, CVD, and PVD, especially in high aspect ratio features. This means ALD can deposit films with uniform thickness from top to bottom in deep trenches and complex geometries. Key differentiators include the ability to create ultra-thin films under 1 nanometer with thickness control as precise as plus 0.1 angstroms. ALD also achieves perfect conformality, delivering 100% film coverage in structures with aspect ratios greater than 100.1. Another advantage is that thermal ALD avoids plasma exposure, eliminating ion bombardment damage to sensitive devices, making it ideal for delicate applications. Lastly, ALD operates as a digital process. Film thickness is determined by the number of cycles, not by process time, enabling unmatched control and repeatability. This makes ALD essential for modern, high-performance semiconductor manufacturing. ALD, applications and advantages. Atomic layer deposition, or ALD, is becoming increasingly critical in advanced semiconductor manufacturing. Its adoption is rapidly accelerating, especially in sub-5 nanometer process nodes, where extreme precision and conformality are essential. ALD is also crucial in 3D NAND flash memory fabrication, where it ensures uniform deposition across complex topographies. Furthermore, it plays a vital role in the production of FinFET and gate-all-around transistors, which require atomic-level film control to maintain performance at smaller geometries. The ALD equipment market reflects this growth, with a strong compound annual growth rate of 14.2% projected from 2023 to 2030. By 2030, the market is expected to reach $8.5 billion, driven by advanced logic and memory applications. When comparing ALD to CVD and PVD, ALD stands out for its excellent conformality and atomic scale thickness control. However, its main limitation is lower throughput compared to the high throughput capabilities of CVD and PVD.